The question is, could you do an example on adding two 2D vectors by the parallelogram/triangle method? We'll see in a little bit that the parallelogram and the triangle methods are fundamentally the same. There are some differences in the details. This is the example that I have selected here. There are two two-dimensional forces, F1 and F2, acting at the same point. We have placed the origin of a two-dimensional Cartesian coordinate system at that point. The force F1 has a magnitude of 40 Newton and acts at 30 degrees to the positive y-axis, and force F2 has a magnitude of 60 Newton and acts at 50 degrees to the negative y-axis. The question is to determine the resultant of these two forces, F1 and F2. We want to use the parallelogram method. The first step is to sketch the parallelogram that goes with these two forces. So how do we do that? Well, we'll take the end of force F1, that will be the head of force F1, and first draw a line parallel to F2, right? And then we take the head of F2 and draw a line parallel to F1. With the point where these two lines meet, we have completed the parallelogram. Here is my parallelogram. Now what do? Well, we connect point A to point C and define the diagonal AC. And the theory says the diagonal AC is the resultant force of F1 and F2. In the picture, I have also marked a couple of angles, angle theta and angle alpha, which will help us define the direction of the resultant force F, but we'll come to that in a second. First, let's go ahead and find the magnitude of F. In order to do that, there are two triangles that we could consider, triangle ABC or ADC. I'm going to consider triangle ADC. And now I'm going to come back and apply the law of cosine in order to find the magnitude of the resultant force F. In other words, the length of the side AC. So here are the two laws that go with the triangle that we talked about in an earlier video. Here's the law of cosine that we're going to use right now. And here is the law of sines that is going to be useful in a second. Now looking at this triangle one more time, the length AD is 60 Newton, right? Length CD is equal to the length AB, which is 40 Newton. So we know the lengths of these two sides. So if you can find the angle between these two lines, then we can find this length of AC using the law of cosine, right? So let's go ahead and find this angle. Well, how do we do that? Well, one way to do that is to make the following observation. Line AB and line CD are parallel to each other, right? So we are interested in finding this angle. Now you might recall from your high school math that if you have two lines which are parallel to each other and there's a third line that runs through the two lines, then this angle plus this angle is 180 degrees, right? So we are interested in this angle. So if I can find this angle, which is angle BAD, then I can find this angle. Now coming back and looking at this point A, right? This angle plus this angle plus this angle is 180 degrees, right? And therefore this angle BAD, is 180 minus 30 minus 50, which is 100 degrees. And therefore angle ADC is simply 80 degrees. To be systematic, let's go ahead and summarize what we know. AD is 60 Newton, DC is 40 Newton, angle D is 80 degrees, AC is F, which is the magnitude of the resultant force. Now applying the cosine law, AC squared equals AD squared, which is that, plus DC squared, right, minus 2 times AD times DC times cosine of this angle between the two lines. Now substituting numbers for the parameters in this equation, we get a value of 66.1 Newton for F. As part of defining the direction of the resultant force F, let's first find this angle theta. So theta is one of the three angles of the triangle that we have considered in the earlier slide, right? So now I'm going to use the law of sines in order to achieve this. So once again, considering that triangle ADC, AC divided by sine of angle at point D, right? AC divided by sine D equals CD divided by sine theta, right? We just found a value for AC in the previous slide, which is 66.1 Newton, right? So 66.1 divided by sine 80, remember the angle at point D is 80 degrees, right? Equals 40 divided by sine theta. So you rearrange this in order to find a value for theta. Theta works out to be 36.6 degrees. Remember the way we define the direction of a vector, right? We want to define the direction in terms of an angle measured from the positive x-axis. So alpha here is one of those angles. Alpha is an angle measured from the positive x-axis to the resultant vector f. We know that this angle plus this angle plus this angle is 90 degrees, right? And therefore alpha is 90 minus 50 minus 36.6, which is 3.4 degrees. In some problems, when you make a sketch of the parallelogram, you are not really sure whether the sketch you have just made is the correct one or not. Well, what do I mean by that? My sketch of the parallelogram could have been such that the line AC could have ended up above the positive x-axis like this, right? Because at this point it's just a sketch, right? We haven't done any calculations yet, and therefore it is possible that your sketch was actually a little incorrect, right? So how do I know whether I got it right or wrong? Well, you will know in the end. This number right here will tell you that. Here we got a positive value for alpha, and therefore my sketch is correct. If the line in my sketch ended up above the positive x-axis, then I would have gotten a negative number for alpha, which I will illustrate in a little bit after completing this problem in the next slide. Alright, now how do we describe the direction? There are two ways to do. Method 1 is to indicate the direction in terms of an angle measured counterclockwise from the positive x-axis, which will be 356.6 degrees. So you could say the resultant force is 66.1 Newton at 356.6 degrees. Method 2 is to describe the direction in terms of an angle measured in the clockwise direction. So in this case, I'm going to use a negative sign with the angle. So you will describe the resultant force as the resultant force is 66.1 Newton at minus 3.4 degrees. Alright, I promised to revisit this issue of what will happen if we start with a parallelogram that is incorrect. Here is a sketch of the parallelogram that is incorrect. AC has been drawn above the x-axis. And in that case, this is how your calculations would have progressed. It's pretty easy to follow. I'll let you follow, but let me point out a few important things here. I'm still going to consider the triangle ADC. The first thing I'm doing here is to find this angle D, and that works out to be 80 degrees, and the details are exactly identical to what we did earlier. The second thing I'm going to do is to find the magnitude AC, the length AC, which is the magnitude of the resultant force. And here are the details, and the steps are once again identical to what we did earlier. We're still marking the angle that goes with the triangle as theta. In other words, theta is the angle of this triangle at point A, right? And I'm still marking the angle that the resultant makes with the x-axis as alpha, but of course this time the alpha has been marked above the positive x-axis. Alright, so the next thing we're going to do is to find this angle theta using the law of sines, and here are the details. And we ended up having a value of 36.6 degrees for theta. The details are once again identical to what we did earlier. The final step is to calculate a value for alpha, and this is where you will start seeing some difference. So alpha here, right, is theta minus this angle, but this angle is 40 degrees because we know this is 50 degrees, right? And this plus this is 90, and therefore this is 40 degrees. So we need to subtract 40 degrees from theta in order to calculate alpha. So alpha is theta minus 40 degrees, and that works out to be minus 3.4 degrees. In other words, we ended up having a negative value for alpha. And therefore, my sketch is not correct. The line AC has to be below the positive x-axis. Everything else is right. In other words, the magnitude of the resultant force is correct, and the angle now is alpha but measured clockwise from the positive x-axis. All you have to do is to correct the sketch a little bit. So the point here is that there's no need to be precise about making the sketch of the parallelogram. If your initial sketch is incorrect, the final numbers will help you correct it. But to avoid confusions, it's good to be as correct as possible.